I'm Peter Sommerlad, and I talk about int. First question, who has ever used int in their code? Okay, that's all of you, 100%, that's perfect attendance. Some remarks, I'm on some social media, and I also prepared a handout for my talk, which contains more than just the slides. So if you're really eager to learn about what I'm talking today, get that handout. It's on my GitHub, and I will also upload it to the conference slide collection site, but I haven't done so yet. Now, anybody not familiar with that symbol that I'm using in the title, that Z? Okay? So, very few. I will explain a little bit about that. It's the math symbol used throughout for the integral numbers. Now, waiting for the last. In general, my philosophy is less code is more software. I stole that from Kevin Henney, and my goal is to write as little, or let's say, when I became a programmer, I learned that a good programmer is a lazy programmer, writing the least amount of code to get something done. And that sometimes means to actually have very good abstractions and put a lot of work in to make it simpler. So it's not easy to write simple code, but that should be your goal, just in general. Now to the actual topic of my talk. So because I had reviewers in some other contexts where I used that conference talk title who were not familiar with or didn't have the math training or didn't remember it, just some very basic math things. So we have that n with a double line for the natural numbers, and those are those that some people say they were given by God. We can count 1, 2, 3, and they are defined by having each number having a successor, so you never end, so you get into infinity. Now, doing math with just the natural numbers is kind of tedious because you have that successor, which is in C++ called plus plus. But you can define addition. The problem is with addition, you don't have a neutral element, so you cannot form an identity function using addition. Therefore, the natural numbers including 0, and very often when we talk about natural numbers, we just include the 0 and take it as a given, but it wasn't given by God, it's a human invention. And there's a nice book on the history of 0 that I can recommend that, but I forgot the author, so if you might need to search for that. Now, when you have addition, you might want to have the inverse operation, which is subtraction, and with that you end up with negative numbers, and you get into what is called Z, the set of integral numbers, and it's kind of closed on addition and subtraction, and you have plus and minus infinity because there's no end to it. If you can always build a bigger or a smaller one by using addition or subtraction. Now, if you look at int, how it's defined in the language for C++. Anybody claims to know how it's defined? Very, very few hands. Nevertheless, I give some interesting things. It's platform dependent. I used to program in C and C++ when int were definitely 16 bits, and that was the world. Tells a little bit how old I am. Sorry for that, but today we have things like LP32, and if you know those things that are kind of either configuration options for some compilers or at least platform options telling you how long a long is, how long a pointer is, how many bits a pointer has. And for example, ILP64 means integers, longs, and pointers are 64 bits. And typically, what we have now is LP64, longs and pointers are 64 bits, and ints stuck with 32 bits. Because there's just too much code out there assuming that an int is 32 bits. as I wrote code assuming an int is 16 bits. I wrote code in my life where I assumed long would be 32 bits and pointers would be 32 bits, which is no longer the case on modern hardware. And fortunately, since C++20, it's actually guaranteed that int is a 2's complement representation, which means we have a range, if you assume 32-bit integers, from -2 to 31 to up to 2 to 31 minus 1 as the largest number. So it's asymmetrical around 0, which is kind of interesting. And in addition, what makes programming hard using int is that overflow and division by 0 is undefined behavior. And undefined behavior is a curse of a lot of programs. It might just seem to do what you think it does until it doesn't. And that can be arbitrary reason for. So when you write, I worked with the MISRA people on the MISRA C++ guidelines 2023, and their undefined behavior in a safety critical system is something you must not have. And even in an ordinary system, I would say you must not have undefined behavior unless you don't care about your computer exploding in the bad case. Now, it's rare that undefined behavior with ints makes your computer explode, but just consider you're having a memory mapped hardware that controls something dangerous, a dangerous machinery. It can actually destroy lives or your computer. Now, as a corollary, we have unsigned integers, which people pretend are safer to use, partially. We get just a positive range, but also it's limited. It doesn't go until infinity, and division by 0 or modulus 0 is still undefined behavior. And the really bad thing about, especially when I lived in a world when int was 16-bit, unsigned short promoted to unsigned. So it stayed in an unsigned realm because unsigned was the same as unsigned short. Today, unsigned short is 16 bits usually, which isn't actually defined. So let's say u int 16t. If you use that in any kind of expression, it will promote. In addition, arithmetic, normal arithmetic, except for the division by 0 case with unsigned integers, is defined to wrap around to have modular arithmetic. That has its own problematic things, but at least it's to wrap around. Now, I almost solved this thing. If you have this code, you have an unsigned short with a value x of 50,000. What is the type deduced for y when I write x plus 1? So I have two hands. 3. It's int. And that is because we have integral promotion. Now, what happens if you multiply x by x? There's one hand. I will repeat it. You don't need.
Unsigned.
Say it again?
You get an unsigned.
No. If the attempted answer was x times x becomes an unsigned value. No. We have integral promotion like for the plus 1. So x times x gets promoted to int first because it's smaller than int. Int can represent all unsigned short values, so it's promoted to int. I have 50,000 times 50,000 as a signed integer multiplication. And now I need someone with a good multiplication things. It's about 2.5 billion, and that's bigger than 2 to 31. So we have integer overflow. So we have undefined behavior, where, especially when I came from, let's say, I'm programming a 16-bit microprocessor with unsigned u in 16t, and now I port my program to, and where it finally promotes to unsigned, so everything is fine, no integer overflow, just wrap around. But with porting it to 32-bit microcontroller, I end up with undefined behavior. And while preparing this talk just last week on Mastodon, Shafiq Yagmur, who always writes interesting quizzes on the, gave the following example. He made it a bit more obvious. We have two unsigned short values, multiply them. What is the expected answer? A very big number, B, a negative number, C, some kind of hex number, or D, undefined behavior. Now, what do we have? Is it A? Is it B? Is it C? Or is it D? I see more hands with D. Okay. The answer is it's D. I haven't confirmed with Shafiq, but I'm quite sure because we get that integral promotion, undefined behavior, due to overflow of the multiplication, of signed integral multiplication. There's a question, and I think we should use a microphone.
It's actually even worse. If you say unsigned short z equals x times y, even if the multiplication doesn't overflow, you get then ub when it's converted back to an unsigned short.
It's the multiplication will, even if you assign it to an unsigned short, the multiplication will be done as integer, signed integer, so you get the undefined behavior nevertheless.
Well, even if it doesn't overflow in the multiplication, but if the result is bigger than unsigned short, then converting back to unsigned short is ub.
No, that's not ub. Integral conversion is never ub. It's just cutting off things. You get the wrong result, or you lose information, but it's never the multiplication. The arithmetic is the ub. Sorry for that nitpicking, but you can guess I did a lot of studying about to get that at least most of the time right. Now there's another quiz for C, which is also valid C++ in that case, and there are similar things. We also get ub. I actually checked with the C standard to make sure that it actually is, and it would be assigned integer again also for C on 32-bit integers, which is given by the LP64. So we see int is not safe, and we get arithmetic overflow for even very simple operations like negation. Negation has one value that it will give you an overflow. If you take a numeric limits min, so the minus 2 to 31, and try to negate that, there's no corresponding positive value that can representable in the type, so you get overflow and undefined behavior. There are other ugly things with integers and all kind of integers. If you try to shift a value by too many bits, it's undefined behavior. You might think, oh, if I shift 32 bits, I have 32 bits, I just get 0. No, it's undefined. You might get 0 if you're lucky, but only because your compiler thinks, nah, I don't want to make your life so hard by just letting your computer explode. There's a question. Microphone, please. Back to you.
But if I would attach a U to the 32, then it would be okay, right? If the result was also, if I assign it to an unsigned as well.
If you shift by too many bits.
No, I mean, the problem here is that I have an unsigned one, then I shift it with an integer, with a signed integer constant, right? If I also make the constant that I shift by unsigned, then it's not.
Maybe I should have used 33. So putting corner cases on the slide is always bad. So 33 bits would definitely be undefined behavior, regardless.
Even if the constant that I shift by is unsigned?
Yes.
Okay, thank you.
So we also have, and that was a topic, we have silent truncation and widening on assignment. So we might lose information, we might change the signedness on initialization or assignment, and all kind of, with assignment, I'm sticking a little bit with the MISRA guidelines where anything where you have a variable or a storage place where you want to put a value to, which might be a function parameter when you call the function or so on, you get those implicit conversions from most built-in types, but also from the integral number, so all integers. We've seen the problem of integral promotion changing the signedness. U in 16T on current hardware will be promoted to int, which is a int 32T, and that is a problem. We have all these implicit conversions. I can tell you a story. When I learned to program in around 1983 at university, or maybe it was already 84 then, we used Pascal, and there you have floating point numbers called real numbers and integers. And you could not easily convert back and forth. You had to use a corresponding, or characters as well. You had to use a corresponding conversion function built into the compiler to get a value of the other type. And I was hating that, because knowing C or even BASIC, everything just worked, and there I had to work around that I might have used real numbers and integers and try to combine them in an expression. Today, I highly appreciate that this was the case. So Niklas Wirth did something right. Type systems are there to prevent impossible or at least unrealistic coding assumptions. And that is something you should embrace. Implicit conversions are really a curse. In addition to those implicit conversions that are kind of more or less banned, we want implementation. We have those implementation-defined sizes. And let's say most people programming today might have grown up with 32-bit integers, but there are still embedded people just porting their stuff to ARM processors and getting the problem that their assumptions from their previous cores, previous processes no longer hold with the 32-bit world. We might even very soon get to a world where we assume to have everything is 64 bits, and then we get additional problems. Now, more on undefined behavior. Given two random numbers, random values of int, what is the probability, and I'd like you to shout out, what if I divide x, which is a purely random thing, an int, by 0? What's the probability that this is undefined behavior? 100%. 100%, great. What if I divide x by y? If we consider, okay, if y is 0, all x values are undefined behavior, so that's 2 to 32 different values. But there's one extra thing that's undefined behavior. If you have minus 2 to 31 and divide it by minus 1, it's similar as negation, so you get an integer overflow. And that's a case, I would say, I claim broadly without having done any research, 99% of people doing integer division forget about when they try to prevent integer division from having undefined behavior. I did, so I can claim at least my code did. So if you want to prevent undefined behavior with division, remember there's a case that people forget about. It's minus 2 to 31 divided by minus 1, which overflows. And if you have wraparound behavior, you stick with the minus 2 to 31, but that's just luck. It's undefined. Now, x plus y. Any guesses? If it would be unsigned, it would be 50%. With signed integers, due to the sign, you get some compensation. It's half of that, 25%. So roughly, or maybe exactly. I'm not sure yet. So addition is kind of an unsafe operation. Only 75% of the operations are okay. Whoever checked addition for integer overflow before you did? A few, okay. Now, the more interesting thing is, how probable is that if you multiply two random integer numbers, that it is overflowing and getting your undefined behavior? Any ideas? Roughly guess. So I would say it's at least as bad as addition, so 25% is the baseline. Let's say, who is for 50%? More than 50%? Okay, almost all. More than 75%? A little fewer. More than 80%? More than 90%? More than 99%? More than 99.99%. It's actually 7 nines. It's almost for sure that this thing overflows. And consider that. If you would do an AI telling you about, does my code overflow? It will tell you every integer multiplication overflows because it's almost, if you have 7 nines, that's always. It's always. So watch out for multiplication. And I learned that from Sean Parent on one of the social media sites that I don't recommend today. He even did a miscomputation because for unsigned integers, you have even more overflows, but there it's not undefined behavior. But for signed integers, it's a little bit less. And I did the computation. I even wrote a simulation program, so I didn't want to use all the 2 to 64 things to get an approximation. But you can actually compute how probable the undefined behavior is, and it's 7 nines, plus even more. Now that's really, really bad. You better not multiply. Summarize. Who knows from the top of their head what the formula 42 unsigned times minus 2 is? What's the type? Play compiler. Unsigned. Who is for unsigned? A few. Who thinks it's int? Also a few. It's unsigned. And it's a very big number, which I don't want to read out from my notes, but you can look that up. So we have integral promotion, implicit conversions that get you ugly things, but also that the arithmetic operators are defined across types by this implicit conversion. And you have to study hard to get the understanding. When I was teaching C in around 87, 89, let's say 87, 88, 89, last century, getting people to understand the so-called today usual arithmetic conversions was kind of interesting, especially since then the compilers weren't always, before being standardized, weren't all agreeing on what they would actually convert to, with signed and unsigned and bit sizes. Now, implicit conversions, as I told you, I thought it's a blessing, but it's also a curse. So it's not really, it's good and bad. Losing information is bad, especially that conversion to bool and from bool are really, really bad, and MISRA forbids them. We might have narrowing and data loss, and we might get the promotion that gives us changing the signedness of an operation, which is really interesting. We have that undefined behavior. We have the wrapping. People think, oh, that's great, we wrap, we don't have UB. Well, there are some cases where you have UB with unsigned types, but also you end up in situations where you have wrong values. Now, the question is, what is the better wrong value? And I'll show you a little bit later. And the undefined behavior is really, really ugly. Something as primitive as using integers having undefined behavior is really, really a curse. Now, if you look at CPP reference, when the arithmetic operation overflows the behavior is undefined, so overflow is one of the things we get undefined behavior. And there are possible things that might happen. It wraps around, which is what many, many platforms and compilers will do for you. Even numeric limits might tell you that it wraps around on arithmetic. And with the two's complement guarantee, it's kind of the obvious choice for an implementer to provide that for you. But if you really insist, and you can even ask GCC and Clang to generate code, that it causes a trap. A trap is the worst thing because usually that means your program is just killed without even proper exiting or termination. And that might be a good thing, but it might not be a good thing when it's running your car brake system and just shuts off when you try to do an emergency brake or steer-by-wire or whatever. And then there's another interesting thing, and that's often forgotten, and people might not even know it. It's about saturation arithmetic. There are platforms where that's the natural behavior. For example, signal processors might actually implement overflow by having saturation so that they have kind of defined behavior so that if the value gets really, really too big, they just stick to the biggest possible value and continue computing with that, which is kind of more reasonable approach than to have then a very, very small value instead by wrapping around. So that gives a little bit more confidence in the result by still having a wrong result, but a less wrong result than having instead of a very, very large positive number, you have still a very large positive number instead of a negative number, which is a thing. And what's really hitting people who assume just it wraps around is when the compiler detects, oh, the code path will always have undefined behavior, so I just throw it away. And that is what people claim, yeah, my code works perfectly when I don't turn on the optimizer, so the optimizer is wrong. No, it's very probable today. I lived in times when the optimizers weren't good, but today it's almost a certain thing, I would say close to what the probability of undefined behavior with multiplication is, that your code has undefined behavior when the compiler optimizer does something bad to your code. Now, who knows what a trap is? Not all, so I have an extra slide for that. It's comparable to a hardware exception. It protects against invalid operations, so some processes, when you reach let's say an opcode in the memory that it doesn't know what to do about, it might actually stop execution and says, no, something's wrong, and try to reset to that. And it's on hardware level, it might be just implemented with an interrupt. And on a software level, it's very often, that interrupt is very often on operating system mapped to a signal from the header C signal, like, for example, FPE. For illegal arithmetic, like division by 0 might give you a SIG FPE signal, typically terminating your program. Sometimes you might end up with a signal SIG-IL, which is for illegal instruction. And both of those signals on, let's say, Unix-like operating systems will create a core dump, except on a Mac where it's a bit tricky because it's so user-friendly, it never tells you what went wrong. Or it gives you an easy way to tell what went wrong. And some other signaling might be processor flags, depending on what kind of hardware you're on. I'm not familiar enough with all the details of for example, the ARM family of the embedded world. They always use a flag or an interrupt or whatever they do with that. Now the question is, if you want to really write code that works and doesn't have undefined behavior, what can you do? And you want still integer arithmetic. And one option is to actually simulate, I have unlimited range. So I simulate the whole numbers, integers, from minus infinity to plus infinity. And the problem there is you still have invalid operations, because if you divide by 0, what should that mean? It's still undefined. You might get exact results, at least for addition and subtraction. and multiplication, but you don't get overflow because you just extend the numbers. But the representation requires memory. You need enough bits, and usually those bits will be allocated from some dynamic memory. And while it's still big, in principle, you cannot actually represent infinity there because you run out of bits because your hardware is limited. So we don't have infinite memory to represent the bits. Now, the more engineering approach, or let's say one more thing about these, we have big int types in libraries, and especially if you want to do operations with very big integers for security reasons, don't use those big int libraries, use specific libraries for security where correct arithmetic and reasons are timing attacks. Now, rest of the talk is about how can we actually make it better than built-in types without undefined behavior, with spelled out sizes, which is what MISRA actually asks for, with no implicit conversions, except for very reasonable things, and we have to decide what happens on overflow and what happens on invalid operations. And you can guess, we've seen some hints from the CPP reference side. There are actually 3 workarounds that you can have. One is wrap around, have modulo operations. If a thing gets too big, just cut off the lower bits and take that value, and fail for the invalid operations like division by 0. That's impossible you have to decide something. The other thing is always detect that something went wrong, even for unsigned values, and signal that something went wrong. For example, by throwing exception or by erasing a signal, just to say, you ran out of the bounds of your representable types, your result is wrong. And if you want, always make sure that you know that your results are correct. That is another option to do. And the last thing is what I explained is saturation arithmetic. Never have a failing computation, but have well-defined wrong results. For example, if you add and add and add and add, and your number gets too big, you just get the biggest representable number as a result. Never wrap around, so the sign is always correct. And but you will at least have a more reasonable result than just wrapping around. Now with that, if I multiply 50,000 times 50,000 with the 32-bit signed integers, in the first case, wrap around, I get that number minus a very big number. In the second case, you detect the overflow and throw an exception or raise a signal. And in the third case, you just saturate to the biggest representable number that you have. That's the differences. And all 3 are valid approaches to safer integers. And it's your choice to know which one to actually use. Now the question is, can we want to implement that as efficient as the built-in integers in C++? But first, my next slide is, what should we do when we have invalid operations? I tried several options, and I reduced those to actually 2. With saturation, no invalid operations. One thing is use assert macro, and if you define ndebug, you end up with UB, so that's not actually a no-go in my opinion. Even though I'm guilty of having these 3 dots in the assert macro, that's why it says there, definition in the standard. So even in C, so I contributed to C standard, even though I dropped C around 90, 95, somewhere between that. We can throw an exception. There might be people objecting to throw an exception. Therefore, I also had that signal thing, which some processes would generate anyway when you actually divide by 0. The problem with signals is they can be ignored. So like ndebug, you can have a runtime change. Ndebug is a compile time change, but with you can ignore a signal from with a signal system call. So you might actually ignore that. So whenever I use the raise thing, I always have a throw afterwards. So if the raise actually returns to your code because the signal was ignored, you throw an exception to actually check that. I abandoned the ndebug state, and if you really want no except in your code, no exception support in your, maybe on your runtime system, then use saturation arithmetic and you're safe, especially in embedded systems. Now, just to show you a little bit how I made this configurable, I have that I use macros. So if someone tells the library when it compiled, should it raise, and Odin is for overflow detecting integers, I include signal and raise, and the assertion that actually is checked either raises a signal or in any case throws whatever is given as a message. Now, implementing that, there are two possible representation approaches. I gave a talk around a couple of years ago at CPP Now, where I used an enum class approach that gives the representation, the exact same representation as the built-in integers. And on all compilers, it gets the identical code generated, except for when checks are actually needed, then there must be some extra code to prevent UB. And the disadvantage is we don't have constructors that actually check the conversion. So static cast will convert any value to whatever enum you give it to, and it will truncate and everything. It's not undefined behavior, but it will just do that. So I tried, well, can I use class types as well? And with some compilers, you get also identical code, especially those compilers that can pass class types in registers. And there is one exception, and we see that on the next slide, where at least for return types, a class type will always be passed in memory and not in a register. And that's kind of a big pessimization in contrast to ints. Now, this is extracted from Gottwald. This is a very simple thing. I have a very little piece of code, a function declared taking two of these int types, whatever that int is standing for, and trying to call that function and check what happens. And that comes from a main function, therefore I static cast it back to int. And the code generated is put the values in registers, call that add, and then the other addition again happens on the register to get the final result. On MSVC, we see a little bit more. There's more stack frame allocated, and then we have the two numbers in registers, but we also, for the return value, we take an address on the stack where we actually, the function is supposed to store the result, and then it's loaded back into a register. So this is kind of overheadish because it's not using registers directly in return type of that add function. That's the case when int is a class type. Now, if we look at the next slide, if we make it an enum class type, the code is identical, except for the bigger stack frame of MSVC, so there's no overhead for enum class type. And to check, it's exactly the same code if we make that int type an int. So if you look back and forth, you see it's actually the same code that's generated. So for the usual case, optimal things. Now, for those of you who want to actually play with it, I have 3 repositories which, for the different approaches, modular arithmetic, overflow detection arithmetic, and saturation arithmetic, and all 3 come with so we get 6 implementations of all are single header, no hassle in building, so no CMake required. Just get your header on your system and compile things with it. Now, how to implement that overflow detection? That is kind of the interesting part. And we see we have unary minus, all arithmetic operators include, plus the shift operators that can potentially overflow. So the cases for negation, we already told you, division by 0 and the minimum number by -1. We cannot shift too many bits, and there's a little bit more work for plus, minus, and star multiplication, especially because we have a much higher probability and not easy to detect cases when this overflows, actually. Now, one way to do that, rely on Clang and GCC built-in overflow operations. They take a pointer for the result and two values, and it will tell you as a return value, a bool, if it overflowed or not. And if you do it yourself, for example, you're not having GCC or Clang, it's also possible. The simple way is to just use 64-bit unsigned, where you know it won't cause undefined behavior when you add two values, and you cast it back to the unsigned value back to the integer, and now you check if the result is actually still the same, because that cast might actually causing the interpretation to be wrong. And this is true when it overflowed. So this assumes that the size of the operands are actually less than 64 bits, and then you get the overflow in the high-level bits. For the, if it's really the actual result, we can still use the overflow here and detect if it's negative, because then it actually results. And there's more. This is just an excerpt of the code, so there is more than the signed 64-bit case is a little bit more involved, and subtraction is very similar. Now, for the plus operator, more or less what we implement, we check if we add two overflow detecting integers, we require same signedness, so you never mix signed and unsigned operations in your code, and then we actually check what is the bigger part. So we do some arithmetic conversion to the bigger result, but we actually stick with the same sign, so there's no possibility to get a sign change from adding a number. And we use the add overflow, which is a wrapper on the built-in add overflow or DIY implementation. And if that is true, we had an overflow, so we just said addition overflow, and otherwise we can use the result in the corresponding representation type to do that. For multiplication, it's a bit more involved. The classical trick for a 64-bit case is actually you do it a little bit like if you have learned multiplication as I did in primary school. You end up using 32-bit digits and compute the lower digit times the lower digit of the one times the higher digit of the other, and lower digit of the one times the higher digit of the other. And you don't need to multiply the higher digits if they are not, because if they are both not 0, you know you overflow anyway. So that's the first case is if the high bits are of the 64 bits are both non-zero, you know it's true. You know that you overflowed, so you don't have to compute anything. And otherwise, you multiply. If the left part is greater than 0, you have to the higher bits times the low bits. Otherwise, the right part might be greater than 0. You multiply that as well. And now, if that already overflowed by having its highest bit set, which would be beyond the 64 bits, you return true, you overflowed, and otherwise you shift those into the high bits and take the low times low multiplication, add it, and now you still have to detect the overflow because of a sign change, and again, that's possible. So easy peasy some code and use the built-ins if you need to, or just use a library like mine to do that. Now for multiplication, again, it's similar to what we did for addition, so no magic there, just using that overflow detection. And for the shift operator, more or less, we just check that the size of bits is less than the number of bits in the type. And I'm sure this should be right, so the 32-bit would actually be already undefined behavior on the shifting by 32 bits. An interesting part is what I implemented here, promote keep signedness. And that's important if we have, let's say, a uint16t type, compatible type is 16-bit unsigned. I definitely want that operation to be as unsigned and not as a signed operation by promoting it to int. And actually we check that it's both our unsigned types that we represent, so that we cannot actually shift signed integers, which is kind of a good thing not to be able to do. Now implementing all those types is very easy peasy. We have for enum class type is very simple, just adding no discard, so that another MISRA guideline take all results as you need them and not only have side effects when you making that obvious by making all types no discard. And we have checked unsigned integer 8 bits up to check signed integer 64 bits. And again, you can assign it to standard ignore, at least from the C++26 onwards. That's a blessed that you can use ignore instead of casting to void, which is great because I no longer have to explain C-style casts to anybody. The class template implementation can make all operators, instead of putting it in the namespace, putting the operators into the as friend functions or member functions into the class. The only difference is we also have to provide a spaceship operator, and that can be easily defaulted. And also I chose that the represented value is actually a public data member. And first thing is, all values of that underlying integer type are valid for my type, so there's no protection against having an invalid value. And you have access anyway, because I provided explicit conversion operators. And it gives a property to the type that is possible to use it as a template value parameter, or variable parameter is the current terminology. So what was called non-type template parameter, classes with only public members can be used as non-type template parameters. And that's what I said here. And I used a different name in the implementation than value, just to, let's say, make it less probable that accidentally someone is actually accessing the member directly. Now, what should not compile? Mixed signed and unsigned operations using bit operation or modulus on signed integers, and invalid compile time operands and valid operations should compile. Now, can we test for compilability? The problem is hard compile errors are really ugly to test for, because you more or less have to enable that error, build it, check that it fails, and now disable it and check the next thing, or otherwise you won't be able to check those things. The good thing is we can use, if it's representable as an expression that is dependent on a template parameter, another template parameter, we can actually use SFINAE to detect compile time problems. And this requires that we are able to represent our operations with variable template parameters. How can we do that? In principle, just one way to do SFINAE, we define a variable template with a base case. We call it from int compile, so we have a type and some extra template parameter that we default, and then we have a specialization from int compiles where we use void t trick and a decal type where you say, okay, if this expression actually compiles, then this value is true, and that's actually a more specialized version than the base case. And with that, we can check, okay, from int compiles signed character, which is actually a synonym for int 8t, that compiles, but we don't want to compile char 80 because MISRA guidelines tell us the character types are actually not used for arithmetic, and so we want to prevent that char 80 value is actually converted to our corresponding int type with 8 bits, and we check that it's not compiling. And with that trick, we can actually have the static asserts for compilability checks. And that's a simple case. If you want to be a little bit more involved, there's also I show you the underlying principle. I changed it a little bit from void to a very similar thing, just a template that takes any kind of value parameter, which is C++ 20. And again, we have the base case, expression compiles is false, and then somehow we need a version where we have still our t, which is a template parameter, and consume value with some kind of expression. The problem is this expression actually needs to be dependent on t, otherwise it would be a hard failure and not considered as finite. So it must be dependent on the template parameter, and that is true. Now, doing that for every possible expression is kind of very ugly and hard to do. So what can we do? If something is hard in C++, well, you use a C preprocessor. And that's the preprocessor thing, creating a namespace containing that is given with the line number, so namespaces won't be distinct. It will be distinct, and then having that expression compiles thing, and I used a special thing here to use an operator or any kind of operation in between two of the default constructors' values to make sure this expression depends on the template parameter, otherwise we will get a hard error. I tried otherwise, but it must be depend on the other template parameter, otherwise it will be a hard error, and all the thing is moot. And with that, we can actually check that our signed integers do not support the shift operator, and the unsigned integers do support the shift operator, for example. And we are running short on time, so let's go forward. Saturation arithmetic is actually, that's the cool thing to have. Because it cannot fail. It might give you interesting results, but less worse than wrapping around, and it will work for any operation. So if you divide by 0, you just get an approximation of infinity, and that's how it works. Again, saturation integers are all named with an S for saturation, so SU for saturation unsigned, S for saturation signed, and so on. We've seen that for the others. And if you look at the class type implementation, again, looks the same as the overflow detection implementation, except that the definition of the operators are different. Now, how can we implement saturation? For example, if I want to change from a regular integer type that is not identical to the target type, and then I check if it's too small, and if the target is unsigned, I get 0. If it's too large, I get the largest representable value. For unsigned case, or for the signed case, again, I get the minimum or the maximum, and that's how things in general work. And for example, if we want to have the saturation arithmetic for operator plus, actually can use in C++ 26, there is add set, which is the saturation arithmetic operator of left and right, and it gives us a result that is clamped to the actual size of the the underlying type, or we can do it ourselves, which is the classic way. We check if it's overflowed. If it overflowed, we check if the result would have been signed. Then we check if the left-hand side was negative. That means the result must be must have wrapped around and be negative. And with the otherwise, we added two big values and it became positive, the maximum positive value. So that's how we clamped there the value to get there. Now, just to give you a glimpse, C++26 defines four of those operations. We have addition, subtraction, multiplication. We have the division, which is actually not really useful because that will actually still have undefined behavior of divide by 0. Therefore, I'm not using that. I use my DIY approach, checking for 0, and the one other case where you overflow with division. And we have that clamp-like saturation cars where you have one type and try to get it into the other and make sure that you have saturation arithmetic. So once you have overflow detection, saturation is simple. That's why I implemented first overflow detection and did saturation, and then I got a GCC with the saturation arithmetic, so I could even employ those, except for the division part that still has undefined behavior. Now, what's my conclusion? Integral promotion is a bitch. Compile time tests are great until they fail unexpectedly, and it's kind of easy to forget a case, so I'm not, as of today, I'm not 100% sure I checked all the cases of all conversions, and when I get back home and have time, hopefully next week, I will try to figure out if I have some corner cases left that are not perfectly implemented yet, and you will see that on based on updates on my GitHub repositories. I allow mixed type operations, but only with the same signedness, and the result will always be the bigger type, which is kind of natural to expect. And you want to test const code also at compile time, and that actually works. And just to give you a glimpse on how I implemented promote keep signedness, so if you really, really want to do that for your own code, just checking I have a trait called ULT for the underlying type, which works both for the enums and the class-based solution. And if the underlying type is less than int, and if it's unsigned, I use the unsigned case. Otherwise, I use int, which is the regular promotion, unconditionally, always for the smaller types. And if not, it's just the underlying type because it will not be promoted directly. So that's just getting that case right, and there's even a context function doing that for your values, but that's I forgot it in some places during implementation efforts, and it's really required to make sure that you don't accidentally get that unsigned to signed conversion happening. Now that's for you to take home. Questions? I have 2 minutes for questions, if I see correctly.
Please go back one slide.
So there was a question about showing the QR codes. I think the simpler QR code is this one. That gives you all the slides with all the QR codes, and the links are in the PDF as well. More questions? So who is going to try this out? That's my question. At least a few hands. So yeah, I hope I get some converts. Who's checking their code for integer overflow on Monday? A few other hands. Good. Turn on sanitizers. They are not too bad in checking that. Write test cases to see how your code behaves when you have overflows. Especially don't trust any kind of input value. I've seen embedded systems that just read a sensor and do some scaling by multiplication. And that's undefined behavior in the weighting, because the sensor might fail, give you a random number, and then you overflow. Because, as you see, 99.99999% probability of overflowing. Good. No more questions? Okay. Thank you.